All right, let's dive right in. Today, we're talking about something pretty wild, a new mathematical paper that lays out a method for solving problems that, for centuries, were considered literally unsolvable.
You know those math problems? The ones so complicated that for hundreds of years the world's best mathematicians could only get a close enough answer? Well, what if I told you that might all be changing? What if there's now a way to find the perfect exact solution every single time? Let's take a look. So, to really see how this works, every good story needs a villain. And in our story, the villain is an equation, a really monstrous-looking polynomial equation. Just look at this thing. It's an 8th-degree polynomial. And for centuries, an equation like this wasn't just hard to solve. Finding an exact solution was thought to be mathematically impossible. The absolute best you could hope for was a pretty good guess. Okay, so what's the big deal? Why are equations like this so notoriously difficult to crack? Well, it all comes down to the limits of the tools we've been using all this time. So you've got two main ways to attack a problem like this. On one side, you have numerical approximation. Think of it like throwing darts at a dartboard. You can get really, really close to the bullseye, but there's always going to be a tiny bit of error. Close enough is the name of the game. On the other hand, you have the symbolic solution. And that, my friends, is the holy grail. It's not a guess. It's the actual blueprint, the exact answer. Now here's the thing. For almost 200 years, a huge rule in math, the Abel-Ruffini theorem, basically proved that you can't create a universal formula to solve polynomials of the 5th degree or higher. It was a giant roadblock. But the author of this new paper, Murad Sultan Ezouidi, says his method finds a way around that long-standing limitation. And that brings us to the hero of our story, a completely new framework for taking on these so-called unsolvable problems. So what makes Ezouidi's theorem so different? Well, for starters, it doesn't guess. It uses this really clever step-by-step recursive process. You can almost think of it like opening one of those Russian nesting dolls. Each step uses the result from the last one to get you closer and closer to the real core of the equation, all with perfect symbols, not fuzzy approximated numbers. Okay, talk is cheap, right? Let's actually see this thing in action. We're going to take that monster polynomial from the beginning and run it through this new process step by step. So here's the game plan. It's basically 3 steps. First, we create some new symbolic terms based on our original equation. Then, we use a special recursive formula to figure out what each one is one by one. And finally, we use those results to put the puzzle back together. I know, it sounds a little abstract, but trust me, the outcome is shockingly simple. Okay, step 1. We plug all those big, messy numbers from our polynomial into the theorem's formula. It does its thing, churns through the calculation, and the very first symbolic coefficient it spits out is 0. Huh. Okay, that's interesting. But hey, it could just be a coincidence, right? A fluke? Let's see. So, we move on to step 2. We take that first result, feed it back into the formula to calculate the next coefficient. And believe it or not, what we get is, yep, another 0. Okay, wait a minute. Something is definitely going on here. This is starting to look like a real pattern. And here's where it gets really beautiful. We can just fast forward because the process just keeps confirming the pattern. We run the calculation for the 3rd coefficient, the 4th, the 5th, all the way up to the 7th, and every single time, the result is exactly the same. A perfect, clean 0. Not close to 0, not some tiny decimal, exactly 0. So we've got this whole string of zeros. What in the world does that actually tell us? This right here is the big reveal. All those zeros aren't just a neat party trick, they are the key that unlocks this whole thing. Because every single one of those special coefficients we calculated turned out to be 0. It's like the theorem just cancels out all the complexity. It lets us see the original equation in a completely new and way, way simpler light. And there it is. Our terrifying 8th degree polynomial, the one that looked totally unsolvable, it was just a simple equation, x minus 1 to the power of 8, in disguise the whole time. The theorem just ripped off the mask. And once you see that, the solution is just obvious. The exact answer is x equals 1. No guesswork, no close enough, just a precise, elegant, symbolic solution. Okay, so solving one tricky equation is really cool, but what's the bigger picture here? Why is this a potential game changer?
Well, let's put this into perspective. Where classical methods would get tripped up or have to oversimplify, Ezouidi's theorem gives us a much deeper look at the equation's actual structure. Higher degrees used to be a nightmare, but for this new process, it doesn't really matter. It systematically bypasses the very limitations that have defined algebra for centuries. So what are we really looking at here? We're looking at a method that's universal. It can work for polynomials of any degree. It's robust. It handles even the toughest, most extreme cases. It's exact. It reconstructs the roots perfectly, no approximation needed. And maybe most important of all, it's independent. It's charting a brand new path away from the old rules. And that leaves us with a fascinating thought, doesn't it? We just saw how a problem that seemed impossible got completely unraveled by just looking at it differently. It really makes you wonder, what other impossible problems in science and technology are just sitting there, waiting for someone to come along with a completely new angle?